Hi guys. So today we are going to do a very interesting topic called number system, and it's one of the highest scoring topics. Looks intimidating, but it's not. And every year you can expect at least two to three questions in every slot. We'll again do it in three levels. First, we will do the concepts and the fundamentals. Level two will be previous year questions, which are a lot, almost around 35 questions. And then we will do level three, which is the advanced level. And by then, we can be very sure that we can ace this topic. So let's start with level one. Before we start, there are a few very basic things that we all should know, which is basically what are the different groups of numbers. So if you talk about natural numbers, these are 1, 2, 3, 4, 5, and so on, right? Then there are whole numbers, thanks to an Indian that we got introduced to zero. And when we add that, it becomes whole numbers, all right? Then we have integers, where we also get introduced to the negative numbers up to infinity and minus infinity. Again, this also goes to infinities. And then we have rational numbers. Any number that can be expressed in P by Q form is called a rational number. For example, let's say 3.6, which can be written as 36 by 10, or you can, reduce it to the smallest form, but it can be written in P by Q form. Or let's say we have a number 10.12345 and so on, and let's say it keeps on repeating after 5. So this is the way to express 5 bar. It basically means 10.12345555 and so on. It will never end, right? So this looks like it cannot be expressed in p by q form, but it can be. How? Let's take a simple example. 10.3 bar, let that be x, multiply both the sides with 10. This will become 103.3 bar, because there are so many that it's like you can assume that it goes till infinity, right? So let's subtract these two. 10x minus x is 9x. This is 103.3 bar minus 10.3 bar. So in this side, you can see that this is basically 93, and this is basically 103 and 33 so on, and this is 10.33 and so on. So this side will be 0, this will be 3, this will be 9. So it becomes 9.00 or 93. And on this side, we have 9x. So x is basically 93 upon 9 or 31 upon 3. So yes, it can be expressed. Similarly for this, if this is x, how will I multiply it? 10203040. So 1, 2, 3, 4. 1000x will be, you will shift this 101234.5 bar. And now I will again multiply it with one more zero and shift it. This is the trick we use. 5. Now you can subtract it. So 1, do it very carefully. 1, 2, 3, 4 zeros will come as it is, but this 10 minus 9 will be 9. And here it is 102345.5 bar. And this is 1012, wait, 101234. 10, okay, 1, 1. Let me rewrite. 101234.5 bar, and this is 101234.5 bar. This will be 0, 1, 1, 1, 1, 1, and 9. So this basically becomes 91111 x. Sorry, this is correct, 9000, and this is 91111, right? So x is 9111 upon 9. This is still p by q form. So they're all your rational numbers. Then finally we have irrational numbers, anything that cannot be expressed in p by q form, can't be, let's write it like this, cannot be in P by Q form. For example, root 2, this is like 1 point, it will just keep on going. You can never write it in P by Q form. Root 3 also. Let's take a interesting example. You know pi, which is 3.14, and it just keeps on going. So is it rational or is it irrational? This is also irrational. Although we do write it 22 by 7, but that is just an approximation we take. It is actually, it cannot be expressed in P by Q form. So pi will also be irrational. And then there are real numbers. Real numbers is basically rational plus irrational. Everything that can be seen, that can be observed, real. And then there is imaginary, which you know, when we use iota, root of -1, it becomes imaginary. All right. This is like basics that we should know. Then there is divisibility rules. How do we know that a number is divisible by something? We know 2, that last digit should be even. We know 3, sum of digits should be divisible by 3. We know 4, last digit divisible by 4. Is that correct? No. Last two digits have to be divisible by 4. All right. It feels like that because let's take an example of 1, 2, 3, 4. It looks like that it should be divisible by 4, right? But it's not because it's not. When you look at it and divide by 4, it is 3 and then 0. So 34 and then 8, 16, 24, 32. So it's not, right? But it looks like that because 34 is not. That's why. If it was 1, 2, 3, 2, we would have said that last two digits are divisible by 4. That's why the entire number is divisible by 4. All right. So this is something that you should remember. 5, again, last digit should be either 0 or 5. Correct? Because it's 5, 10, 15, 20, and so on. 6, again, 6 is 2 into 3. So divisible by 2 and divisible by 3. That is how we check. 7 is very interesting. We'll come back to that. 8, last one digit, no. Last two digit, no. Last three digits divisible by 8. That is how we check. All right. 9, again, sum of digits divisible by 9. All right. 10, obviously, last digit 0. All right. 11 is interesting because sum of odd place digits minus sum of even place digits has to be divisible by 11, or it can be 0 also, right? So 0 is also divisible by every number. So for example, let's take a random number 1, 2, 3, 4, 6, 8. All right. Now I want to see if it is divisible by 11. Take these numbers 1, 3, and 6 and take odd place numbers 8, 4, and 2. Doesn't matter. You can take 8, 4, and 2 also before. Odd, it can be positive, it can be negative. I am only concerned about the number that comes. So this is 10, 8, 9, 11, 12, 13, 14, which is 4 or -4. So since 4 is not divisible, therefore the number is also not divisible. 4 is not divisible by 11, therefore n is not divisible by 11. All right. Now make it divisible. How? We need to get rid of this 4. So how do I get rid of this 4? Maybe I can make 6 reduced by 4. If I can make this 2, 1, 2, 3, 4, 2, 8 will be divisible by 11. Why? Because now instead of 6, this will be 2. And since it is 2, this whole number will be reduced by 4 and will come out to be 0. So my job is done. Other ways, let's make this -4 as -11. All right. So how do I make that? I can give it, is it correct? Let me just quickly check again. If I make this 2, this becomes 6, and 6 minus 14 is not -4, correct? Wait. So this is wrong because there's negative involved. Let's think it again. I want this minus 4 either to be 0. So I want to add 4 here, right? So how do I add 4 here? I can make this as 7. Then my job will be done, because then this will become 14 and this entire thing will become 0. So 1, 2, 7, 4, 6, 8 is divisible by 11. Okay. But if I take, let's say, I added 4 to make it 0. Let me subtract 7 more to make it minus 11, and then also my job will be done. So I need to subtract 7. So basically I can add these things by 7. Let's make this as 9. Okay, then also my job will be done. So 1, 9, 3, 4, 6, 8 will be divisible by 11. How? This is 7. So instead of 3, this is 7. So this basically becomes 8, 9, 10, 11, 12, 13, 14. This is 14. So this becomes 0. And when I took 9, instead of 2, this is 9. So this is basically minus 9, 10, 11, 12, 13, 13 and 8, 21. So 10 minus 21 is minus 11. My job is done. So you get an idea how we can play with numbers to make them divisible, because we know the divisibility rule. Again, if there is 12, it has to be divisible by 3 and it has to be divisible by 4. This you can think about any numbers then. 13 is also very interesting. So let's take 7 and 13. The idea is any number, let's say, let's pick the same number 1, 2, 7, 4, 6, 8. How do I check for 7 and 13? Start making groups from right and make groups like these. Start from right, make pairs of 3, 3, and so on. And then let's take another, let's increase this number. So this is also another group. Doesn't have to be 3. I will just keep on making groups in pairs of 3. Last, there are 2 left, then this will also become a group. And then you take these groups from right and subtract and add. So 4, 6, 8 minus 1 to 7 plus 95. Now, if you calculate this, you get to know that 468 minus 1 to 7, that means 341 plus 95. So that means 436, correct? Now 436, I have to check if it is. I'm checking for, let's say I'm checking for 13. So now this we can check. So 13, 26, 39, 52. So I know 3s are 39. So 46. Again, 3s are 39. So 7 is the remainder. So this is not divisible. That's why this is also not divisible. You want to make it divisible, then I need to either reduce 7. So 9, 5, 1, 2, 7, 4, 6, 1 will be definitely divisible, because I am reducing this entire number by 7. So the remainder is 0. This is divisible. Other way, 7, make it touch 13. So 5, 7, 8, 9, 10, 11, 12. Sorry, 6. So if I add 6, then my job is done. How can I add 6? I'll add 6 somewhere here. Okay. So since I cannot add this 6 now, it will become 10. Then grouping will be disturbed. So 6, break it into 3 and 3. So make this add by 3, which is 4, 5, 6, 7. And where is the 6? Make this add by 3, which is 9. So 95127798 will also be divisible by 13. So you got an idea, right? How we can play with numbers using this divisibility rule. Again, let's quickly check for 7 also. I want to check if 9163572 is divisible by 7 or not. How do I check? Again, make groups from here. Don't make groups from here. If you start making from left, then this won't work. You have to always make it from right side. Okay. So 572 minus 163 plus 9, which is basically 418. Let's see if 418 is divisible by 7. 7 sevens are 49. 7 6 are 6 are 36, 42. So 7 5s are 35. And this is 68. 7 sevens are 49, 56. 7 8s are 50. 7 5s are 35, 68, and 7 7s are 49, 7 8s are 56, 7 9s are 63, So again, 5 is the remainder. So you can say this is not divisible by 7. How to make it divisible? Since get rid of this 5, how do I get rid of this 5? I can reduce this to 2. I can do so many. I can reduce 3 from here, 2 from here, right? There's so many possibilities. So accordingly, we can play. And if I want to add something, then make 2, add 2 more. 2 can be added here. We can make this also as 4, or we can reduce this by 4. Anything you can do. Just you should know the divisibility rule. All right. Let's move ahead. Other than that, there is no limit to divisibility, but if I get 15, I know it is 5 and 3 I need to take care of. So other numbers we will take care like this. But also remember, it doesn't work with other than 7 and 13. It won't work. This trick is only valid for 7 and 13. So you can write it in your notes. Make groups of 3 from left and alternatively subtract and add. All right. Same is for same as 7. And then check the divisibility. That's why I always show it with example. Language can always be confusing. In your notes, write this example. All right. Check. All right. So this won't work with 17. So this rule only for 7 and 13, not for others. For example, if I tell you that, check 9173572 if it is divisible by 17. So you will again, if you use it, you should not use it, but I just want to explain. So if you do this, 572 minus 173 plus 9, it comes out to be 408. And 408 is divisible by 17. But original number is not. All right. So you get an idea that this trick will not work other than 7 and 13. Okay. Let's go to part 2. Okay, we will do the entire number system in 6 parts, and that was part 1. Now we're going to do it in second part, which is factors, LCM, and HCF. All right. So the idea is that what are factors? Any number that can divide the original number will be its factor. For example, if I take 120, I can, or let's say 120 can have multiple factors. One is always a factor. 120 itself is a factor. That is true. A number will always be its own factor. One will always be its factor. Other than that, I can write it as 1 into 120. I can also write it as 2 into 60. So 2 is also a factor. 60 is also a factor. Similarly, I can write it as 3 into 40. So 3 is also a factor. 40 is also a factor. There's so many ways, right? So let's break it down into its native form. So 120 can be written as 2 into 60, 60, 2 into 30, 30, 2 into 15, 15, 5 into 3. So I can write it 2 to the power 3 into 3 into 5, right? So this is basically standard way of writing a number, and then you can quickly tell how many factors it will have. I will go on to that also, but I want you to know that how do you break it down into these prime factors along with this power. So let's say a general number can be written as P1 to the power A1, P2 to the power A2, P3 to the power A3, and so on. This is your general way of representing here. P1 is 2, P2 is 3, P3 is 5, A1 is 3, A2 is 1, A3 is 1. All right. Let's take a simple example, 36. Now I can write it as 6 into 6, correct? So if I write it as 6 into 6, can I say that this is 2 into 3 into 2 into 3, or 2 square into 3 square? All right. Now let's find out the number of factors of 36. So I can say that 36 can be written as 1 into 36, 2 into 18, 3 into 9, sorry, 3 into 12, 4 into 9, 6 into 6, right? There's so many ways of writing this, correct? Now look at it. Every time 2 takes powers, and interacts with 3 with any power, we actually get a factor. So 2 can take 0, 2 can take 1, 2 can take 2. 3 can take 0, 3 can take 1, 3 can take 2. They have all the choices. So 2 has 3 choices, 3 has 3 choices. Total, there will be 9 combinations. So 9 factors will be there. So number of factors formula is A1 plus 1 into A2 plus 1 into A3 plus 1 and so on. This you can note down. This we should always remember. And let's understand what is the logic. Why is it coming 9 factors? Because here I saw for n equals to 36, which can be written as 2 square into 3 square, number of factors will be 2 plus 1 into 2 plus 1 or 3 into 3, 9. Now let's manually find it out. 2 to the power 0 will definitely be a factor. 3 to the power 0 will also be a factor, but that is also 1, right? X to any power, any number to the power 0 is 1, right? So I am not writing 3 to the power 0 because it is also 1. It's a repeat. 2 to the power 1 is a factor. 2 to the power 2 is a factor. 3 to the power 1 is a factor. 3 to the power 2 is a factor. 3 to the power 1 into 2 is a factor. 3 to the power 2 into 2 is a factor. 3 to the power 2 into 2 to the power 2 is also a factor. See, nothing is getting repeated so far. Similarly, 2 into power 2 into 3 is a factor, correct? This we have not covered now. And 2 to the power 2 into that I've covered. So 1, 2, 3, 4, 5, 6, 7, 8, 9. See, these are the 9 factors which I got from this formula. So this you will remember that n can be written as, if n is written as p1 to the power a1, p2 to the power a2, p3 to the power a3 and so on, then this is the formula for number of factors. This also you note down. All right. Now next thing is we just did number of factors. We will also do sum of factors. Again, if you look at n, which was 36, which is 2 square into 3 square, if I write it like this, every time they interact, we will get a factor. 2 to the power 0 will interact with 3 to the power 1, one of the factors, correct? So how do I write? This is basically, when you expand it, it will bring all those 9 terms and you can see it as sum, correct? Now, the way to look at it is, this is a GP, okay? In a GP, you know that sum of a GP is A r minus 1 upon r minus 1, which is r is the common multiple, A is the first term. If you don't know, we will cover it in sequence and series, so you can check that out there. But A in this case is 2 to the power 0, which is 1. R in this case is 2. And total number of terms are 1, 2, 3. So can I write this as A into R to the power n, sorry, r to the power n minus 1 upon r minus 1. N is number of terms. So 2 to the power 3, 1, 2, 3 terms, minus 1 upon 2 minus 1. And this is 1 is the first term, 3 to the power 3 minus 1 upon 3 minus 1, because here also there are 3 terms. So if you look at this, can you see it written like this? Right? So from here we get to our formula that sum of factors can be written as p1 to the power a1 plus 1 minus 1 upon p1 minus 1, p2 to the power a2 plus 1 minus 1 upon p2 minus 1 and so on. This is your sum of factors and you just saw how we derived it. Again, remember n is p1 to the power a1 into p2 to the power a2 and so on. So this is your second formula that you need to remember. All right. It looks intimidating, but it's so easy. When as soon as I get a number, I can quickly write it as 2 to the power 2 plus 1 upon 2 minus 1, 2 to the power 3, 3 to the power 2 plus 1 minus 1 upon 3 minus 1. So in this case, p1 to the power a1 plus 1. So p1 is 2, power is 2. So P1 to the power 2 plus 1 upon 2 minus 1. Because P1 is also 2. Okay, now let's look at product of factors. So product of factors is basically when we multiply all the factors and then what we get as a result is the product. It is n to the power number of factors upon 2. So in our case, when we took 36, which was 2 square into 3 square, and we got our all the factors as 2 to the power 1, then 2 to the power 2, 3 to the power 1, 3 to the power 2. We got 2 into 3 square, 2 into 3. We got 3 into 2 square. So 1, 2, 3, 4, 5, 6, 7, 8. Which one is left? We got 3 square into 2 square. That is remaining, right? 3 square into 2 square. Now, when I make a product, the powers will get added, correct? So, power of 2 will be, add the powers, 0 plus 1, 1, plus 2, 3, plus 1, 4, plus 1, 5, plus 2, 7, plus 2, 9. Similarly, 3 powers will be 1 plus 2, 3, 4, 5, 6, 7, 8, 9, right? So in this case, you know the number of factors was 2 plus 1 into 2 plus 1, right? Once you got number of factors as 3 into 3, 9, you will write simply product of factors will be 9 to the power 2 or 36 to the power 9 by 2. Take that power inside, root 36 to the power 9 or 6 to the power 9. Now just to match the options, we can write it as we want, but you can see that this makes sense. So this is the formula for product of factors. One last thing that is remaining is in how many ways can I write it. For example, I can write it 36 into 1. I can write it 6 into 6. I can write it 2 into 3. I can write it 4 into 9. I can write it like 12 into 3. There's so, sorry, not 2 into 3, 2 into 18. There's so many ways of writing this number. How do we find out what are the number of ways to, write this particular number? So the formula is simply number of factors upon 2. For example, in this case, if I see number of factors was 9, so because it is a perfect square, it will be number of factors plus 1 by 2 if it is a perfect square. This is basically called number of ways of writing as a product of 2. Right? As a product of two numbers. This is basically the idea. Number of factors plus 1 by 2 if it is a perfect square, because you saw it's 9, right? So 9 plus 1 by 2 or 10 by 2, or there are 5 ways. And you can see the 5 ways here. Any other way you will make, it will be repeated. In case it is not a perfect square, for example, let's take an example of 120. So 120 can be written as 2 into 60, 2 into 30, 2 into 15, 3 into 5, or 2 cube into 3 to the power 1 into 5 to the power 1. Again, find out the number of factors, 3 plus 1 into 1 plus 1 into 1 plus 1, or 4 into 2 into 2, 4 to the 8 to the 16. So 16 is the number of factors. Let's find out all the values and we will revise also. Sum of factors, a to the power, what was the first term? 2. So 2 to the power 3 plus 1 minus 1 upon 2 minus 1. Next is 3. 3 to the power 1 plus 1 minus 1 upon 3 minus 1. And 5 to the power 1 plus 1 minus 1 upon 5 minus 1. So this is 2 to the power 4 minus 1 upon 1. This is 3 to the power 2, 9, 9 minus 1, 8 upon 2. This is 5 to the power 2, which is 25. 25 minus 1 is 24 upon 4. And 2 to the power 4, Always remember 2 to the power 10 is 1024. 2 to the power 5 is half, 5 and 2. 2 to the power 4 is half, so 2, 5, 6. So 2, 5, 5. Got it? Sorry, 2 to the power 9 is this, 2 to the power 8 is this. So that's why you need to remember one power so that you can find out 2 to the power 9 quickly. But in case of 2 to the power 4, you know, it's like 16. So 16 minus 1 is 15, 4, and this is what? 6. So it basically becomes 15 4 is 60, 60 into 6 or 360. And now finally, if I want to find it, in how many ways can I write it as product of 2? How many ways as product of 2? You can write it down. It's basically n upon 2, not n plus 1 by 2, because it is for perfect square. So n is number of factors. Okay, number of factors upon 2. That's why I took this example. So number of factors was 16. So 16 by 2 is 8. Let's verify. Let's just for our understanding. 120 in 8 ways. How? 1 into 120. Next, 2 into 60. Next, go in a pattern. 3 into 40. 4 into 30. And be sure that we're not repeating. 5 into 24. 6 into 20. Again, got repeated, right? Then 7, no, 8 into 15, yes, because I use this. Then 9, no, 10, yes, 12 into 10, 11, no, 12, yes, but we have already done. Then what else? We need 8, right? 1, 2, 3, 4, 5, 6, 7. 1 is remaining. Yeah, 6 is remaining, right? So here it will be 6 into 20, but this is 2 into 60, so it's different, right? So we got 8. So I hope this is clear. Now, we will quickly revise LCM and HCF, and I'm sure that you guys are very well aware of it. But still, let's try to feel the importance of it. We know HCF is highest common factor, and we know LCM is lowest common multiple. So guys, don't focus on lowest, focus on multiple. So any number, its LCM, let's say there are two numbers A and B, their LCM will be more than A, more than B, and HCF will be actually, it's like common factor. What is common between the two? So it will always be less than A and B. Although they sound like highest and lowest, but it's the opposite. So let's understand it taking our two numbers 36 and 120. We know that this is 2 square into 3 square, and we know 120 came as 2 cube, right? Yeah, 2 cube into 3 into 5. When you take LCM, you take the highest powers of all the numbers. So 2 has highest power of 3, 3 has highest power of 2, and 5 has highest power of 1. Correct? So this is your LCM. HCF take lowest power, which is common. So 2 square is common, 3 to the power 1 is common, 5 not common, so nothing, right? So this is 3 into 4, 12, which is the HCF, and this is 8 into 9 into 5. 8 5 is 40, 40 into 9, 9 into 36, 360. So LCM is 360, HCF is 12. So I told you now, 12 is actually less than 36 and 120. 360 is more than 36 and 120. And one more very super interesting thing, product of numbers is actually equal to product of LCM and HCF. All right. So in this case, 36 into 120 will actually be equal to 12 into 360. And we can see that it is true. And it is only true for two numbers. Don't try it for more than two numbers. Only true for two numbers. And this can be used, like, for example, let's say we get a question that LCM and HCF of two numbers are, this and this, or there's some relation between them. One of the number is this, then find the second number. So you can use product of numbers is equal to LCM into HCF. All right. Now let's try to understand the significance of it. Let's say I have total 10 oranges, and I have, let's say, I have an example, 40 oranges and 30 apples I have. And I want to make boxes. Every box should have similar content. Then how many boxes will I have? I know number of boxes will be less than 40 and 30 for sure. So this is automatically an HCF thing. Now 40 can be written as 2 into 20, 2 into 10, 2 into 5. And 30 can be written as 2 into 15, 5 into 3. So it is 2 into 3 into 5, and this is 2 cube into 5. HCF is common. What is common? 2 is common, 3 is not common, 5 is common. So 10. So I can say there will be 10 boxes. All right. And in every box, with logic you can see, but the idea is divided by HCF. So 40 by 10 or 4. So basically 4 oranges, and 30 by 10. So 3 apples. So every box will actually look like this. There will be 4 oranges and there will be apple. Let's denote with Y. And there will be 10 such boxes. All right. Another example, if I go to office every third day, this is an example to feel what is LCM meaning. And my friend goes to office every fourth day. When will we go together? Obviously, it will be more than 3 and more than 4. So this case will be of LCM 3 into 4, or this is 2 square, or this 3 to the power 1. To get the idea, 12. So 12th day we will be together, and then 24th day, and then 48th, sorry, 36th day, and so on. Keep on adding 12. So these will be the days when we'll be together in the office. All right. There's a very nice example for the same. Let's say there are 3 bells. All right. And every bell rings at interval of 12, 15, and 18 minutes. So there are 3 bells and they keep on ringing. First bell rings after every 12 minutes, second after every 15 minutes, third after every 18 minutes. If they ring together at 6 a.m., let's like 6:30 a.m. for the first time, all right, when will they ring, let's say, for the fourth time together? All right. So you know that they will ring together at certain time, but that will be way more than 12, 15, and 18. Again, LCM, then we need to find out LCM. So what is 12? 4 into 3. So 2 square into 3. What is 15? 3 into 5. What is 18? 6 into 3, which is 2 into 3 square. Now LCM will be highest power of 2, which is 2. Highest power of 3, which is 3. Highest power of 5, which is 5. All right. So 4 into 9 into 5, 9 5 is 45 into 4, which is 90 plus 90, 180. So 180 minutes or 3 hours. I know they will ring for the second time after 3 hours of 6:30 or 6, 7, 8, 9, 9:30 a.m. They will ring for the second time. For the third time, again add 3 hours at 12:30 now p.m. Then fourth time they will ring at, again at 3 hours, 15:30 p.m. or 3:30 p.m. PM doesn't really complicate things when we are adding too small, but it becomes complicated when we ask for larger numbers. For example, if I'm telling you that when will they ring for the 14th time? Okay. Now I know that for the 14th first time they rang at 6:30, and for the 13th time, that means 13 into 3 hours have passed out for them to ring for the 14th time. Correct? Why 13? Because every 3 hours they ring for after 3 hours they ring for second time. Again 3 hours third time. So for 14th time they will be 13 into 3 hours passed. Correct? For second time 3 hours passed. So 2 minus 1. For third time 2 into 3 hours passed. So 3 minus 1 into 3 hours. That's why 13 into 3 hours, which is 39 hours. Now 39 hours is what? 6:30 they rang for the first time, then 24 hours, then again 24 hours. So it will be 6:30, but it has been 24 and 24 is 48 hours. But it's not 48 hours, it's less. So come back. So 39, so 9 hours come back. So basically, if I go back 9 hours, this 6:30 will become midnight in 6.5 hours. Remaining 2.5 hours, you have to come back. So basically 10:30, 2.5 hours. Sorry, 9:30. Then if you add 2.5 hours here, this will be midnight. Add 9 hours, it will be 6:30. So at 9:30, they will ring for the 14th time. AM or PM? PM. It's night. Got it? This is how CAT will make simple concepts a little complex for you to understand the depth of the concept. Now, another very nice question could be that how many factors does 2016 have? How many will be even? First part is very easy. Let's just quickly factorize it. 2 ones are 2, 2 to the 4, 10, 5, and 2. So 2 into 252. Now I don't know, I will not do it in exam like this. I'll just keep on doing mentally and write. So this is 2 into 1, 2, 6, which is 2 into 63, which is 3 into 21, which is 7 into 3. So this is 1, 2, 3, 4, 5, 3 square into 7. So this is 2016. So I know number of factors is 5 plus 1 into 2 plus 1 into 1 plus 1, or 6 into 3, 6, 12, 18 into 2, 36 factors. But not all of them will be even. For even, I cannot give 2 a choice of taking 0. If it takes 0, then it will not be even. I need 2 for it to be even. So this time 2 will not have 5 plus 1 choices, but only 5 choices. 2 can take 1, 2, 3, 4, 5, but it cannot take 2 to the power 0. While 3 can take any value 0, 1, 2, 7 can take any value 0 or 1. So 5 into 2 plus 1 into 1 plus 1, which is 30. So 30 factors will be even. Therefore, 6 factors will be odd. And this is how a question will be framed. How many factors are odd? I can't think like that. I have to think even factors because I can play with 2. Correct? Similarly, if it would have asked that how many factors will not be divisible by 3. Correct? So basically, we don't want 3. So 3 has only one choice, that it has to take 0. So it will be 5 plus 1. 7 can again have 2 choices. 3 does not have. 3 has only one choice for it to be not divisible by 3. So basically 6 into 2, 12. 12 of the factors will not be divisible by 3, and therefore 36 minus 12, 24 will be divisible by 3. I can take so many examples, but you get an idea, right? How you can play around as per the question framing. Now let's go to part 3. Part 3, basically we will talk about remainders, and this is where actual number system comes in place, and it's the interesting part. Any number, if you divide by another number, it will give you some kind of a remainder, or it will not give you some kind of a remainder. But in general, I can write any number as a equals to bq plus r, where r is your remainder. A and b and q are dividend, divisor, quotient, but you don't need to worry about all of that. And now if I take any number, let's say, just to explain, 39, and if I divide it by 12, I know 12, 24, 36. Let's take smaller number and let's take bigger here. So I know when I divide 9, 18, 27, 36, so 3, and then 5, 8, 16, 24, 32, so 3. So 3 is here remainder, right? So I can write 395 as 4 into 98 plus 3. So I know 3 will always be less than 4 and it will always be more than 0. So can I say, let's say that this is your remainder r. So r will always be greater than 0 and it will, or it can be equal to 0 and it will always be less than b. For example, in this case, 4, b is 4, q is 98, r is 3 and a is 395. So this is like the basic notation for remainders. Now we'll play around, and one more very important thing that you should know, there's a way of representing it. I can say that 395 gives 3 as the remainder when divided by 4. I can also say the entire thing as 395 gives remainder 3 when divided by 4. Now take your time to absorb, but this is the general notation to write any number. For example, A gives remainder R when divided by B, for A is equals to BQ plus R. So this is your general way, and there are some very interesting factors. For example, A plus B, whatever remainder it gives when divided by N is same as A when divided by n, whatever remainder comes, and b when divided by n, whatever remainder comes. So we can add the two remainders. Similarly, a into b when divided by n, whatever remainder comes is same as a when divided by n into the remainder b, which comes when b is divided by n. So these are two important equations that we always use. Then there is also a very nice concept of negative remainder. What does that mean? So in this case, when I got remainder as 3, I can also say the remainder is minus 1. All right. If I do 394 by 4, I will get the entire same thing, but this time I'll get the remainder as 4. So because the remainder is, sorry, I'll get the remainder as 2. So since the remainder is 2, I can say the remainder is also minus 2. 4 minus 2, right? Whatever is left to make it perfect. So this is the concept of negative remainder. All right. Remainder is 3, but negative remainder is minus 1. Remainder is 2, but negative remainder is minus 2. So negative remainder is basically, just write it down for you to understand, when number is closer to multiple of divisor, you should just know that, in general, we call this as divisor. All right. This we call as dividend, whatever is on the top. And sorry, this is quotient, q is quotient, this dividend divided by divisor. All right. And it's not important, but in question, if it comes, you should know what is what. When number is closer to the multiple of divisor, it is faster to work around with negative remainder. So this is basically the significance of having a negative remainder. All right. Now, how do we use that? So we will come to cyclicity, but I'll just quickly take it here also. Cyclicity, one of the very, very interesting topics of number system, basically the backbone of number system. So let's say I am asked that 7 to the power 100 is divided by 8, then what is the remainder? Please note this question also. What is the remainder? Now, 7 to the power 100 divided by 8, I'm not going to expand 7 to the power 100, right? How do I see it? I know that 7 gives minus 1 as negative remainder, right? So 7 to the power 1 gives minus 1 as remainder when divided by 8. So 7 to the power 100 will give minus 1 to the power 100 as remainder when divided by 8. So answer is 1. 1 is the remainder when you divide 7 to the power 100 by 8. And be comfortable. This is the notation we will use every time. So you understand, you can appreciate why negative remainder is important. Now we will do actual cyclicity, which is very very important. And let's just take some examples. So in remainder, there's a pattern. For example, if I take a question that 2 to the power 100, what is the remainder when 2 to the power 100 is divided by 7? So 2 to the power 1 gives remainder 2 when divided by 7. 2 to the power 2 gives remainder 4 when divided by 7. 2 to the power 3 is 8, which gives remainder 1 when divided by 7. As soon as you hit 1, you are know that things will start getting repeated. 2 to the power 4, which is 16, which gives remainder 7 to the 14, so 2 when divided by 7. 2 to the power 5, which is 32, 7, 14, 21, 28, which gives 4 when divided by 7. So you can keep going on, it will always be 2, 4, 1, 2, 4, 1, 2, 4, 1. So there's a cyclicity of 3 going on around this, and I just need to see that 2 to the power 100, can I make split 100 as cyclicity of 3? So it can be written as 3 into 90, 3 into 33, which is 99 plus 1. All right. So this, I need to find out what is the remainder when divided by 7. This can further be written as this because powers get added. And this I don't need to take care of because the remainder is 1. On this is basically 1 cycle, 2 cycle, 3 cycle, and 33rd cycle will also bring me here. So this will give me remainder 1. This 2 to the power 1, you can see that it gives you remainder 2. So answer will be 2. So remainder is, how will you write? 2 to the power 100 will give you remainder 2 when divided by 7. So this is the concept of cyclicity for remainders, and although it looks like difficult at first, but it's not, it's very handy. And one very important note is that if I say 2 to the power 102 mod 7, this is basically saying that what is the remainder of 2 to the power 102 when divided by 7. So if you look at it, this is basically 3 into 34. That's it. So don't say that answer is 0. Say that it is 34th cycle, so it will end here. So answer is 1. All right. It's just some mistakes students do, but you get the idea, right? So now let's move to one of the kind of intimidating part of number system, but it's not. It's called Euler's theorem, or there's another theorem called Fermat theorem, Fermat-Young theorem, and stuff like that. But we don't need to worry about this because it's basically a special case of Euler only. So we don't need to like really understand that. If we understand Euler, we're done. So what does this say? A to the power psi of n always gives remainder 1 when divided by n. I know, doesn't make any sense, right? So let's understand it slowly. So for example, let's say that I want to figure out what is the, let's take some example. I want to figure out 10 to the power, 3 to the power 100 when divided by 7, what is the remainder? Now I'm not going to expand 3 to the power 100, right? So there is a special way. Now, what is happening is that there is something called psi, which is basically all the numbers which are less than 7 and are co-prime to 7. For example, 1 is co-prime to everyone, 2 is co-prime, 3 is co-prime, 4 is co-prime, 5, 6, less than 7. Okay, so 1, 2, 3, 4, 5, 6 numbers. So I can say phi of 7 is actually 6. So phi of n is basically total numbers less than n and co-prime to n. All right. So here I can say that for any prime number, it is always n minus 1. So phi of n will always be n minus 1 if n is prime. And you can see the logic also. And this is basically Fermat theorem. Whenever your n is prime, it becomes a special case of Euler. Euler is applicable everywhere. All right. So take some 5-10 minutes. Bear with me. You will be able to understand. Once I got psi, I will know that 3 to the power 6 will always give remainder 1 when divided by 7. This is what Euler figured out. Okay. 3 to the power psi of n is always giving remainder 1 when divided by n. Got it? For example, in this case, I was a to the power n, a to the power psi of n gives remainder 1 when divided by n. So in this case, a is 3, n is 7, and psi of n is 6. All right. Psi, phi, whatever it is called. But now I'll use this information and I'll get to 3 to the power 100. How? Can I write 3 to the power 100 as 6 into 6 ones is 6, then 46 is 36 into 3 to the power 4. This I know is going to give me remainder 1. So I don't need to worry about that. Only thing to worry is 3 to the power 4. And what is 3 to the power 4 mod 7? This I can now find with cyclicity. 3 to the power 1 will always give you 3 when divided by 7. 3 to the power 2, which is 9, will give you 2 when divided by 7. 3 to the power 3. Now you don't need to do 3 to the power 3 as 27. Just multiply the last remainder with 3. That will also give you the same answer. So it's a trick. 3 into 2 is 6, which is the remainder. Let's do it. 3 to the power 4. Don't calculate 3 to the power 4. 6. Just take this remainder and multiply it by 3. So 18. And 18 will give you what? 7 to the 14. So 4. Mod 7. Let's do it for practice. 3 to the power 5. Don't do 3 to the power 5. 4 into 3, 12. Which will give you 7, 8, 9, 10, 11, 12, 5. 3 to the power 6. Don't do 3 to the power 6. 5 into 3, 15. Which will give you remainder 1. When now we will stop. Now we know it will repeat. So it's a cyclicity of 6. And 3 to the power 4 will give you 4. So answer is 4. 4 is the remainder when you multiply it, when you do 3 to the power 100 divided by 7. One important thing to note is that this a and n, they both have to be co-prime. All right. A and n are co-prime. This is the only condition that Euler put. So you can only do it as soon as you see this question. You have to see that 3 and 7 are co-prime. That's why I can use Euler. All right. Let's say if you don't know Euler, you don't want to understand Euler, you could have anyway done it with cyclicity. And if you look at it, 3 to the power 6, it has a cycle of 6 going on, right? So I can simply write 3 to the power 100 as 6 into 16 and 3 to the power 4. Now I know there is a cyclicity of 1, so I would have anyway use this. So where did I use Euler? Because I got 3 to the power 6, so I know the remainder is 1. And in this case, this is also coming as 1. So sometimes Euler is very effective, but most of the time we can do it with cyclicity. So let's understand more with more examples. All right. Let's say 5 to the power 100 when divided by 17, what is the remainder? And keep noting all these questions, okay? So now 5 to the power 100 divided by 17. I know 5 and 17 are co-prime. First, always check this. What can I do? I can simply say that let's do 5 to the power 1 gives remainder 5 when divided by 17. In exam, when you're doing it, you don't have to write this again and again. I'm just showing it for understanding. This 25 and 17 table we should quickly write. So 25 will basically give me what? 17 minus 25. 25 minus 17, 5, 6, 7, 8. Right? Then 5 to the power 3, don't do 125. Just simply multiply 8 by 5, 40. And 40 will give you 6 as remainder. 5 to the power 4, don't do that. 6 into 5, 30. 30 will give you 13 as remainder or minus 4 negative remainder. Okay, this is also very handy. Keep on writing. But usually when I get -1, then only I use it. Now what? So I have to keep on doing it till I get 1. Let's try 13 into 5. 5 is a 15. 5 is a 5, 65, and 65 will give me 65, 14. Correct? I can keep doing this This is using cyclicity. But now I will show you how I can do it with Euler. All right. So if you say phi of 17, 17 is a prime number. So 17 minus 1 will be 5 because 1 to 16 all numbers will be co-prime. So now I know that 5 to the power 16 will give you remainder 1 when it is divided by 17. So you will get cyclicity of 16 directly, which I would have got if I continued this. I would have gotten 5 to the power 16 giving me remainder 1. But I got directly from Euler. So you can appreciate what Euler has done. Now 5 to the power 16, let's write 5 to the power 100 in cyclicity of 16. That's the entire logic. So 16 into 8, 8 5s are 40, 48, 8 1s are 8, 9, 11, 12, 128, 16 into 7, 3 are 36, 42, 7, 7, 8, 9, 10, 11, 112. So 16 6 are basically 36, 96. 16 6 are 96 into 5 to the power 4. This I don't need to worry about because Euler told me that the remainder will be 1. 5 to the power 4 I need to care, and that I got 13. So 13 is the answer. What is 13? 13 is basically the remainder when 5 to the power 100 gives remainder 13 when divided by 17. I hope that it's digestible. You are able to understand and appreciate Euler. Let's take another example. What is the remainder when 7 to the power 20 is divided by 21? Again, let's do Euler. No. Why? 7 and 21 are not co-prime. So can't use Euler. Can't. Then what? Cyclicity are always best friends. 7 to the power 1. And this is how I will do it in exam. Okay. 7 to the power 1 is 7. 7 to the power 2 is 49. And I'll quickly write the table so that I don't get confused. 7 to the power 2 is 49, which gives me remainder 7. 7 to the power 3 gives me, again, don't do 7 to the power 3. Just multiply last remainder by 7. So 7 to 7, 49, again 7. Again 7. So every time I'm getting 7. So answer is 7. Every power is giving, when divided by 21, is giving 7 only. So 7 to the power 20 will give me remainder 7 when divided by 21. So no requirement of Euler. All right. Very interesting. And I can do so many examples, but let's cover the entire number system and keep on practicing so much that we get very comfortable. But let me take one more example. All right. So I'll take 4 to the power 40 divided by 9. What is the remainder? So 4 to the power 40 divided by 9. Again, 4 and 9. First, always see 4 and 9 are co-prime. Great. I will use Euler. So phi of 9. Should I say 8? No, because it's not a prime number, right? Phi of n is n minus 1 only when n is prime, not always. Okay, so find out. 1 for sure, every time. 2, yes. 3, no. Why? Because 3 and 9 have a common factor, right? 3 itself. So they're not co-prime, so not 3. 4, yes. 5, yes. 6, no. Because 6 is 3 into 2. 9 is 3 into 3. So 3 is common. 7, yes. 8, yes. 9, no. We have to see less than the number. So 1, 2, 3, 4, 5, 6. So phi of 9 is 6. And 4 to the power 6 will always give remainder 1 when divided by 9. I know this looks like why are you doing it so fast, because I've seen it so many times. So once you do at least 10 questions, you will see that it's pretty manageable. That's what Euler says. Whenever you get phi, a to the power phi of n gives remainder 1 when divided by n. Now what? Now nothing. It's done. 4 to the power 40 can be written as 4 into 6 into 6, 36 into 4 to the power 4. And this gives 1. I need to care about 4 to the power 4. Cyclicity. 4 to the power 1 gives remainder 1. 4 to the power 2 gives remainder 4 into 4, 16. 16 by 9, 10, 7. 4 to the power 3. Don't do 4 to the power 3. Just multiply 7. Last remainder with this. 4 into 7, 7, 14, 21, 28. 9, 18, 27. So 1. 4 to the power 4. I would have stopped here because I know that it's going to be 1717 and so on. But let's do it. 4 to the power 4. Again, 1 into 4. So, sorry, it's not like that. It's 471, and then again I'm getting 4. 4 to the power 5. Is it correct? When I did 7, 14, 21, 28, 9, 18, 27, so 1, 4 to the power 4, which will give me 4, and then 4 to the power 5, again 16, which will give me 7, 4 to the power 6, 7, 14, 21, 28, which will give me 1. So it's basically, that's why. This is 4. So 471, 471. This is the cyclicity. Cyclicity of 3. Because I know it has to trail at 1. So it has, because I got again 4, I was like 1714. What is happening? So I made a mistake. It's 471. So now 4 to the power 40. We got it to till 4 to the power 4. So I know it is answer is 4. So 4 is your remainder. How do you write that? 4 to the power 40 gives remainder 4 when divided by 9. All right. And if you don't want Euler and if you forget about Euler, you could have done it directly with cyclicity also. You saw that 4 to the power 40 divided by 9, you saw 4 to the power 6 is 1. So you could have directly written 4 to the power 40 as for this, and you know that cyclicity is anyway, it is coming 1. So you could have like skipped the part, you could have skipped this part, and you could have directly done cyclicity and used this. So every question can be done by Euler, can be done by cyclicity also. For example, 3 to the power 47 divided by 5. I know 3 and 5 are co-prime. So I know I could have, let's do it with cyclicity first, okay? So 3 to the power 1 will give you 3, 3 to the power 2 will give you, and you don't do this when you're finding remainders, okay? So 3 to the power 2 is 9, which will give you 4 as remainder. 3 to the power 3, again, don't do 3 to the power 3. 4 into 3, 12. 12 will give you 2 as remainder. 3 to the power 4, 3 into 2, 6, which will give you remainder 1. Now it will get repeated. So cyclicity of 4. So 3 to the power 47 can be written as 3 to the power 4 into 1, 1. So this is 44 into 3 to the power 3. And this is taken care of 1. And this is 2. So answer is 2. Got it? Very easy. Now, if we do it with Euler, let's say 5 of 5. 5 is a prime number. So 4. 3 to the power 4 will always give remainder 1 when divided by 5. So Euler just told us what we found out from cyclicity. Now again, we will do the same thing and we will get there. So I hope that Euler theorem is understood, and it's not like we will have to use Euler. We can always use cyclicity, but sometimes Euler might come in handy. So you should know. Let's go to part 4, and we've done first 3 parts. So half of the concept is done. Now we'll go with our part 4, which is base system. It's very, very easy. So we use 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 for all the numbers in the universe. So we follow a base of 10. We have 10 digits and everything is around that. So that is called base of 10. Similarly, in computer language, there is only 0 and 1. So this is called base of 2. All right. And we can now play around from these bases, and we can use this concept of what is this number in base 6? What if this number is in base 8 converted into base 7? Something like that. So let's look at any number. Let's say 2459. How do you know that this is in base 10? Because it is 2 into 10 to the power 0, 1, 2, 3 plus 4 into 10 to the power 2, 5 into the 10 into 10 plus 9 into 10 to the power 0. Correct? This is basically 2000 plus 400 plus 50. This is like the basic of addition, and we get to 2459. 259. Now, similarly, if there is a number, let's say 101101, it is basically, if we have to look this in a way, so it becomes 1 into 2 to the power 0, 1, 2, 3, 4, 5. So basically, if I have to convert any number into base 2, this is the process of converting that number. And the process gives me this number. For example, let's say I want to convert 2459, which is in base 10. This is like one of the way of denoting. And I want to convert it into base 2. What will I do? I'll take the numbers and I'll multiply with powers of 2. Okay. And in that way, I will get to this number. Now, if I want to, for example, I want to see that this number is in base 2. Instead of writing all of this, we will write this. And we want to convert it to base 10. Either we'll convert things into base 10 or we'll convert base 10 into something. So the thing is, we can see it as 1, just like there was powers of 10, here there will be powers of 2. So power 0, 1, 2, 3, 4, 5. So 1 into 2 to the power 5 plus 0 into 2 to the power 4 plus 1 into 2 to the power 3 plus 1 into 2 to the power 2 plus 0 into 2 to the power 1 plus 1. This is how we expand it. So this is basically 2 to the power 5 plus 0, 2 to the power 3 plus 2 to the power 2 plus 0 plus 1. Always remember 2 to the power 10 is 1024. This comes very handy. Okay. And 2 to the power 5, I know it will be half of this. So 5 and 2, 8, 4 and 1, which is 8, 9, 10, 11, 12, 13. So 5, 2, 5. So I can now say that 101101 to the power, in base 2 is same as 525 in base 10. And this is the entire significance. So we started using other digits, but in world of base 2, there were only 1 and 0. Now, similarly, let's look at one of the questions. For example, I want to convert, let's say there is some base 5. What does that mean? We can only use digits as these 5 digits we can use. So let's take any random number, okay? But the rule is we can only use these digits because we're in a world of base 5. So let's say 23140 or 323140. This is my number. Now I can see I cannot say what base it is. It can be base 5, it can be base 6, it can be base 7, it can be base it can't be base 4 because then you can only use 0, 1, 2, 3. So it can be anything in the world. But I know it is in base 5 because it is saying it like that. Okay. Now I want to convert into base 10. How will you do that? Again, 5 to the power 0, 1, 2, 3, 4, 5 plus 2 into 3 to the power 4 plus 3 into 3 to the power 3 plus 1 into 3 to the power 2 plus 1 into 3 to the power 4 plus 0 into, 1 plus 0 into 3 to the power 0. I'm not going to calculate, but you got the idea, right? Now let's do opposite. We will go from base 10 to, let's say, base 7. So 156 in base 10. I want to see what is it in base 7. Now there's a trick to that. Just divide the number, whatever it is, by whatever base you want to convert it into. Let's divide it by 7, and this is how you should denote it. So you will get what? 7 2s are 14 and 2s are 14 and remainder is 2. Similarly, take 22 divided by 7, 7 14 21. Remainder is 1. Now divide 3 by 7. This will give you 0. As soon as you get 0, you can stop, and then from this side, you can say it is 312 in base 7. 156 in base 10 is 312 in base 7. Take your time, absorb it. I know it looks weird in that way, but there are questions in CAT which have come in the past which have used this concept, and it's very easy once you've done it. Now convert 500, which is in base 10, to something in base 6. Okay. You can pause the video, try it yourself, or let me just do it here. So 500 in base 10, and I want to convert it into base 6. Now this is not 5 into 10 to the powers. You're going from 10 to outside. When you're coming to base 10, you use that. Okay. So this will be basically 500 divided by 6, not like this. Write it like this only. So this is basically 500 divided by 6. 6 8s are 8, 6 7s are 36, 6 7s are 8 5s are 40, 48, 20, 6, 12, 18. So remainder is 2. Now 83 divided by 6. It's not equal, but I'm just writing it like that. 6 ones is 6, so 23. 6, 12, 18, 19, 20. So 5 is the remainder. Now 13 divided by 6. 6 2s are 12. Remainder is 1. Don't stop here. 2 divided by 6, 0. And remainder is 2. As soon as you get 0, then you stop. So 2152 in base 6 is same as 500 in base 10. This is enough practice. It's not as complicated as it looks. How will CAT use it? It will take it one level higher. So if 234 in base B equals 69 in base 10, find B. We are moving to base 10. So first technique. Moving out of base 10, second technique. So now basically it is what? It is 2 into b square, because b to the power 0, b to the power 1, b to the power 2. 3 into b to the power 1 plus 4 into b to the power 0 is 69. So 2b square plus 3b plus 4 is 69, or 2b square plus 3b minus 65 is equals to 0. It's a quadratic. And I hope that you're aware of quadratic. Otherwise, watch the quadratic equation video, basics of algebra. But let me just quickly repeat it. If you know ax square plus bx plus c equals to 0, there is something called determinant, which is b square minus 4ac. And then x will be minus b plus minus root b square minus 4ac upon 2a. All right. So here also you can do that. Or you can play around. 65 into 2 is 130. 130 can be written as 13 into 10, which is 13b minus 10b minus 65, or take b common, 2b plus 13, take 5 common, 2b plus 13. So it is 2b plus 13 common and b minus 5. So b can be either minus 13 by 2, not possible. Base can't be, base has to be integer. So b is 5. So that's your answer. So number system is huge in terms of concept. This is end of part 1, and we will cover the remaining in part 2, and you can find it on the same playlist. So do check that out. Happy learning, guys.